Hello everyone, welcome to quick revision series of strength of materials. In this video, I'll be discussing about principal stresses and strains. First, I'll be discussing the definition of principal stress. Next, we'll be seeing the transformation of stresses by numerical method and graphical method. Similarly, transformation of strain by numerical method and graphical method. Now, let's see what is principal stress. Principal stress is nothing but the maximum or minimum normal stress acting on any plane. That plane must be in such a way that it has zero shear stress. There should not be any shear on that plane. In general, there are two principal planes, or for 3D system there may be up to 3 principal planes. Now, let's see the transformation of stress by numerical method. In first case, we will be discussing one-dimensional stress. In case of one-dimensional stress, there is either only one tensile stress or one compressive stress. Now, if this is the criteria, there is a tensile force acting on it. Now we have to find what will be the stress in this plane, which is theta degree in anti-clockwise direction. Okay, we will be getting normal stress as sigma dash as sigma cos square theta and shear stress as sigma sin theta cos theta. We get this by if we take components of this force in normal direction and shear direction. This is stress. Find force like sigma into area, finding force and dividing it in normal direction and shear direction, we will be getting this formula. Derivation is not that important, but we should remember these formulas. See, the normal stress is sigma cos square theta. Theta is anti-clockwise direction with this plane. And shear stress is sigma sin theta cos theta, which is nothing but sigma by 2 sin 2 theta. Now let's see 2D stress case and how to use this formula. See, we have derived this formula by assuming some certain sign convention. So, in order to find the correct answer, we should follow this sign convention. We derive formula by using sigma x and sigma y as tensile forces and tau xy is in this direction. And we have considered theta as anti-clockwise angle with sigma x plane. Remember, with sigma x plane, and the tau xy dash and sigma x dash obtained will be in this direction. Remember, be careful while substituting the value of theta. In some cases, they will be giving this angle. So, we have to find this angle, that is 90 minus theta dash, and substitute in this formula. We should not substitute directly theta dash in this formula. And in some cases, they will be giving plane this way. If they give plane this way, according to our formula, theta is in anti-clockwise direction with sigma x plane. So, this is sigma x plane, theta is in anti-clockwise direction. So, we have to substitute this as theta in this formula. Okay, I hope you understood this sign convention part. This is the most important part in this principal stress chapter. So, you can follow any sign convention, but while using this formula, particularly these two formulas, we have to follow this sign convention only in order to find the correct answers. So, we have seen the sign convention part. Now, let's see these formulas. The sigma x, sigma y are the normal stresses. Tau xy is the shear stress. Theta is angle with sigma x plane. We have seen this in the sign convention part. Then the normal stress acting on this plane is given by this formula, and shear stress acting on this plane is given by this formula. Okay, we have to remember these formulas. These formulas are very important. Remember this negative sign also, and don't forget to remember the sign convention part. It is the most important thing to remember. Now, for principal plane, the shear on that particular plane is 0. That means in order to find the angle where the principal plane occurs, By equating this shear stress equals to 0, we can obtain it. By equating it to 0, we will be getting theta p, that is angle where principal stress occurs. See, there are many planes in between with many angles theta. There is one plane such a way that on that particular plane there is no shear, that is theta p. We obtain like principal stresses sigma 1 and sigma 2. Here sigma 1 is major principal stress and sigma 2 is minor principal stress. This is theta p, and other plane will be like, see, in this case, if this is principal stress, other stress will be at 90 degrees with this stress. So, see, other plane will be 90 degrees from this principal plane, that is theta p plus 90 degrees. Okay. If one principal plane is at theta p, other principal plane will be theta p plus 90 degrees. If we see this condition, this is also a 2D stress condition. But in this case, like unlike before case, there is no shear acting on these planes. Okay. If we observe it clearly, on this plane there is only normal stress and there is no shear acting. Similarly, on this plane also there is only normal stress and there is no shear stress acting. That means these two planes are principal planes only. So, by substituting tau xy, shear equals to 0 in before formula, we will be getting normal stress on this plane as this one and shear stress on this plane as this one. Now we came to conclusion that these sigma 1 and sigma 2 are principal planes, and if these two are principal planes, then at a particular angle theta, normal stress and shear stress are given by these formulas. Now let's see what is maximum shear stress. See, for finding maximum shear stress, we know that tau xy at a particular angle theta is given by this formula. For this to be maximum, we have to maximize sin 2 theta. For sin 2 theta to be maximum, 2 theta must be 90 degrees. So, theta must be 45 degrees. That means from this particular principal plane with 45 degrees angle, there is a plane such that on this plane tau is like maximum shear acting on this. Okay. Remember, if theta p is the principal plane, if we take a 45 degrees angle from that principal plane, we will be getting a maximum shear plane. Okay. By substituting this 45 degrees in this formula, we will be getting tau max as sigma 1 minus sigma 2 by 2. That is difference between two principal stresses by 2. Okay. Now let's see on the maximum shear stress plane what will be the value of normal stress. By substituting theta equals to 45 degrees, we will be getting, see, if we substitute theta equals to 45 degrees here, then it will be cos 90, which is 0. So, we will be getting sigma as sigma average. So, on this plane, sigma will be sigma average, that is sigma 1 plus sigma 2 by 2. Remember, in case of maximum principal stress plane, on that plane shear is 0. But in case of maximum shear stress plane, tau max plane, sigma is not equals to 0. In this case, sigma will be sigma average, sigma 1 plus sigma 2 by 2. Remember this, don't confuse. In case of principal stress, tau will, shear will be 0, maximum normal stress, shear will be 0. But in case of tau max plane, sigma won't be 0. Okay, sigma will be sigma average. Till now we have seen where the principal stress occurs, where the principal strain occurs, and what is the value of maximum shear stress. Now let's see what are the values of sigma 1 and sigma 2, that is major principal stress and minor principal stress. For major principal stress, we will be substituting plus, and for minor principal stress, we will be substituting minus. This formula is obtained by substituting tan 2 theta p equals to 2 tau xy by sigma x minus sigma y in transformation of stress formula. First we have seen the transformation of stress formula, this one. By substituting in this formula, the values of sin theta and cos theta, we will be getting sigma 1 and sigma 2. Okay. As we substituted in the transformation of stress formula only, the sign convention will be same as that formula only. That is, sigma x and sigma y are tensile and tau xy is in this direction. If they give compressive stress, then we have to substitute minus sigma x. Okay. Now we know that tau max is sigma 1 minus sigma 2 by 2. By substituting sigma 1 and sigma 2 with these values, we will be getting tau max as this formula also. This tau max is also the radius of Morse circle. Till now, we have seen the numerical analysis. Now let's see the graphical method. This method is also known as Morse circle method. We will be drawing the Morse circle by using same loading condition as numerical method. The loading condition is something like this: sigma x, sigma y and tau xy. Now, I'll explain in brief how did I obtain this Morse circle. The y-axis will be shear axis and x-axis will be normal stress axis. If we take this plane, on this plane there is sigma x and tau xy. So, sigma x is normal stress and tau xy is, in y-axis, that is the shear stress. So, this point is sigma x comma tau xy. This is in anti-clockwise direction. Here I have taken anti-clockwise as positive. And on this plane, this particular plane, we have sigma y and tau xy in clockwise direction. So this particular point is sigma y comma tau xy. Joining these 2 points, we will be getting center of Morse circle. Okay. With this point as center and this particular length as radius, if we draw a circle, then we will be obtaining a Morse circle. This is how to draw a Morse circle in brief. Here in Morse circle, every line from the center of the Morse circle indicates a particular plane. Okay. In this case, this particular plane is major principal plane, whereas this particular plane is minor principal plane. This particular A is a major principal stress value, that is sigma 1 comma 0, whereas B is sigma 2 comma 0. Okay. This A comma 0 is center of circle. This is given by sigma x plus sigma y by 2 or sigma 1 plus sigma 2 by 2. We have to remember this. Sigma x plus sigma y is equals to sigma 1 plus sigma 2, which is equals to any normal stress in some particular axis, that is sigma x dash plus sigma y dash. If we remember this point, then if in some questions they will be giving sigma x and sigma y and they will be giving one principal stress. If they ask other principal stress, we can easily find this. If you want to know how we have obtained this, we can see in this circle. So, if we observe these two triangles, we have these two are opposite angles, so these two angles are equal. This is tau xy and this is tau xy. This is radius of circle and this is radius of circle. So these two lengths are equal. If we write OC plus OD, that is sigma x plus sigma y. OC we can write as OB plus BC. OD we can write as OD. We can write as OA minus DA. So by congruent triangles concept, we have seen these two lines are equal, as this is radius of circle and this is radius of circle. BC and DA are also equal. So these two are equal. That means which is equals to OB plus OA. OB is nothing but major principal stress. OA is nothing but OB is nothing but minor principal stress. OA is nothing but major principal stress. That means sigma 1 plus sigma 2 equals to sigma x plus sigma y. This is small derivation. So we have seen what is A, what is B, and what is center of Mohr circle. Now let's see what is E. This AE is nothing but the maximum shear stress plane. That means on this plane, the shear stress is maximum. We know that on maximum shear stress plane, sigma is sigma average. So we can observe in this case also. If we take what is, points, coordinates of E, this will be, x coordinate will be A, that is sigma x plus sigma y comma sigma y by 2, comma, the y coordinate will be tau max. Okay. Now let's see what is radius of Mohr circle. It is given by this formula. If we observe sigma 1, we know that sigma 1 is given by sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 whole square plus tau xy whole square. If we see this thing in Mohr circle, it is OA is nothing but from O to small a plus radius of circle. That is, this is center plus radius. Okay, use major principal stress. Center minus radius, that is till center minus radius, use minor principal stress. Okay, this is radius of Mohr circle. We know that this is also equals to tau max. We have seen few minutes ago. We also know that tau max is sigma 1 minus sigma 2 by 2. We can observe this here also. See, sigma 1 is major principal stress and sigma 2 is minor principal stress. Subtracting sigma 1, that is OA minus OB, gives us dia. Dividing it by 2 gives us radius. That means tau max is equals to radius of Mohr circle, which is equals to sigma 1 minus sigma 2 by 2, which is equals to this formula also. Okay. Now let's draw Mohr circle in case of pure shear condition. Pure shear condition is nothing but on that particular plane there won't be any normal stress acting. So in this condition, if we take, this is origin, we know here sigma x is 0 and sigma y is 0. So sigma x point will be 0 comma tau and 0 comma minus tau. According to the same sign convention, we used it before. Clockwise is negative and anti-clockwise is positive. So 0 comma tau and 0 comma minus tau. Pointing these two and with 0, center as joining these two, we will be getting origin as center of Mohr circle. With tau as radius, we have to draw a circle. That means in case of pure shear condition, origin will be center of circle and radius will be tau and major principal stress will be plus tau and minor principal stress will be minus tau. We can also find this by using formula also. We know that center of Mohr circle is given by sigma x plus sigma y by 2. In this case 0 plus 0 by 2 comma 0, that is 0 comma 0. Whereas radius is given by square root of sigma x minus sigma y by 2 whole square plus tau x whole square. By substituting this, we will be getting radius as this formula only. By substituting major principal stress is center plus radius, we will be getting this one. Center minus radius, we will be getting minor principal stress as minus tau. By using formula also, we will be getting same values only. Now let's see how to draw Mohr circle in this condition. in this particular condition, sigma x and sigma y are both equal to sigma, and there is no shear stress acting. So here sigma is tensile load. So it will be somewhere here, sigma comma 0, and sigma y is also here only, and there is no shear stress. So this particular Mohr circle will be a point circle. Okay, in case of point circle, there are infinite number of principal planes. That means every plane is a principal plane. This is a point circle. Every plane we take on this point, like on every point, the stress is sigma comma 0. That means every plane is a principal plane in this case. So there will be infinite number of principal planes. Okay. Now let's see how to draw Mohr circle for this condition. Here they gave sigma x as 15 and sigma y as 5, and there is no shear acting. So first point will be sigma x. First we will be pointing sigma x comma tau x. This as tau xy is 0, it will be 15 comma 0. And sigma y point will be this one. Joining these two at 10 comma 0, there will be center with radius 5. We have to draw a circle. Okay, this circle looks like this. As both are tensile forces, this is to the right side of the origin. If they give compression forces, it will be to the left side of the origin. Okay. Now let's draw Mohr circle for this condition. This is a triaxial loading. In case of triaxial loading, remember, there won't be a 3D Mohr circle diagram. There won't be a sphere. We have to draw Mohr circle for 5, 20 condition, 10, 20 condition, and 5, 10. See, Mohr circle looks something like this. For 5, 20, it will be 5 and 20. This way. And for 10, 20, 10 will be somewhere here. This will be this way. And for 5, 10, this will be this way. Mohr circle looks something like this. There won't be any 3D figure for triaxial loading. Remember this. Now let's see some questions. In this question, they are asking, draw a Mohr circle such that there is no plane where normal stress is 0. Now they are saying there should not be any plane where normal stress is 0. That means we should not include origin. Mohr circle looks something like this. See, for suppose if we include origin in Mohr circle, see, there will be one plane at least such that normal stress is 0. See, here in this case there are two planes where normal stress is 0. Or if we take something like this, there are two planes again where normal stress is 0. So if we exclude origin from our Mohr circle diagram, there will be no plane where normal stress is 0. Say here in this case, at every plane there exists some normal stress. There is no 0 normal stress plane. Okay, this will be answer. Now let's modify this question. Instead of normal stress, if they ask shear stress, what should we do? See, previously as normal stress is in x direction, we have drawn it this way. Now as shear stress is in y direction, in order to have a plane such that there is no shear stress, we can draw it on y direction, like with y axis as center. Now if we observe this condition, in this condition they are indirectly saying there is no principal plane, because there is no plane such that there is zero shear stress. So this is not, Directly we can say this is impossible condition. By drawing Mohr circle also we can say this is an impossible condition, because we know the properties of Mohr circle, that is Mohr circle always lies on normal stress axis. I mean center of Mohr circle always lies on normal stress axis, and it will be symmetric about normal x-axis. In this case, if you observe, it is not symmetric about x-axis, and this center is not lying on y-axis. In both the cases, we can say this particular case is impossible, like with shear stress as 0 is an impossible case. Now let's see other question. Draw a Mohr circle such that in a plane of maximum shear, normal stress is 0. That means where there is maximum shear, the normal stress is 0. That means tau max, comma, 0 must be point. Okay. We know that in case of maximum shear, this tau max will be tau average. But they are in this question, they are asking this tau average must be 0. Okay. We also know that this tau average is center of Mohr circle. That means the circle looks something like this. See, if we observe this circle, in case of maximum shear, there is 0 normal stress. Okay, this is the condition. This is a condition of pure shear also. Like in case of pure shear condition, tau max will be tau, and this condition satisfies. And there may be other condition like sigma x is tensile force and sigma y is compression force with same value. So in this condition also we will be obtaining this circle. This case satisfies. I hope with this you got a brief idea like how to draw Mohr circle. Till now we have seen the stress analysis. Now let's see strain analysis. We know that strain is independent parameter and stress is dependent. This depends on strain actually. We can find strain, but we can't find stress directly. In order to find stress, we have to find strain and then calculate stress. So, if we have the values of strain, we have to use this formula in order to find the stress values sigma 1 and sigma 2. Okay, this formulas we obtained it by solving these two equations. We know that if this is a stress condition, the strain will be sigma 1 by E minus mu sigma 2 by E. This is like by using Hooke's law, extended Hooke's law, we got this formula. I have discussed in this third video of quick revision series. And epsilon 2 will be this. By solving these two equations, we will be getting sigma 1 and sigma 2. In general, practically we will be finding the stress value sigma epsilon 1 and epsilon 2. And by substituting these two, we will be getting stresses. Okay. Now, similar to transformation of stresses, now let's see transformation of strains. This transformation of stresses and strains, these formulas will be almost same, but instead of tau xy, we will be writing tau xy by 2. Okay, remaining all the formulas will be same. Instead of tau xy, we will be writing phi xy by 2. See, here also instead of tau xy, we will be writing phi xy by 2. Remaining everything will be same. See, for writing tan 2 theta p, we will be equating this to 0. So, we will be getting tau xy by 2, tau xy by 2. Cancelling these two, we will be getting this formula. Okay. If we know that theta p is principal plane, for obtaining second principal plane, we will be writing theta p plus 90 degrees. Okay. This theta p1 and theta p2 are the principal planes. Only difference is that instead of tau xy, we will be writing phi xy by 2. And remaining everything will be same. See, now let's see why we are writing tau xy like phi xy by 2. If we take a particular plane, due to shearing action, it got deformed this way. So, for suppose the deformation will be phi by 2 and phi by 2. Like total deformation will be phi, but deformation of this plane will be phi by 2 and this plane will be phi by 2. So here we are writing like shear equation for a particular plane. So we will be considering phi by 2 as a shear in this case. shear condition. Okay. In graphical method also it is almost same, but in like instead of taking tau in y-axis, we will be taking 5 by 2 in y-axis plane, and in the x-axis plane it will be epsilon only, like shear normal strain only. So in many in many exams they will be asking question like what is radius. In this case radius will be 5 max by 2, remember this, and dia will be 5 max. This is important. Like this is small thing only, but we'll be confusing it with stress thing, and we'll be writing radius as 5 max. In this in case of strain analysis, radius is 5 max by 2. Okay. Remaining everything will be same. Center will be sigma 1 plus sigma 1 plus sigma 2 by 2. Here it will be phi 1 plus phi 2 by 2. See, here we wrote instead of tau xy whole square, we are writing phi xy by 2 whole square. Everything will be same. These are some concepts in principal stress and strain. Basically, this is a like easy chapter only. If we remember the sign convention properly, and if we remember these formulas, I mean these particular 8 to 9 formulas, this chapter is very easy chapter. This 1D stress formula also we have to remember. This transformation of stresses formula, and what is principal plane and how we obtain the principal plane, and what is maximum shear stress plane, and how like maximum shear stress plane is principal stress angle base 45 degrees angle is important, and at maximum shear stress plane this normal stress won't be 0, and it will be an average of 2 normal stresses, and we have to know what are the properties of Mohr circle, and what is radius of Mohr circle. And other thing we have to remember is, I forgot to say this, if theta is like angle, we at theta, if we want to find the normal stress and shear stress, in case of Mohr circle, like if we see in Mohr circle, we have to take 2 theta, and in case of principal strain we need to remember this formula, and in case of principal strain, similar to principal stress, what is I mean at transformation of strains, we have remember this formula and this formula. Remember, only difference is instead of writing tau xy, we have to write phi xy by 2. Remaining everything will be same. And how to like formulas for sigma, I mean principal strains. And major thing to remember in this principal strains is radius is not phi max. It is phi max by 2. We have to remember this. Okay. With this, I will be ending this video. If you find this video useful, please share it with your friends. I will be uploading videos regularly. If you like my content and want to revise with me, you can subscribe to my channel. Thanks for watching.